Hello students, today is our last lecture on boundary layer theory, and today we are going to see the effects of pressure gradient on boundary layer. Okay, so to analyze the effect of pressure gradient, what we do is we consider the boundary layer momentum equation. So that is the boundary layer x momentum equation. Y momentum equation was neglected. So the momentum equation inside the boundary layer is simply rho, or basically it's the x momentum equation, steady state x momentum equation without that mu times del 2 u by del x2 terms, because that is negligible. Okay, now we say that what happens to this Governing equation at the wall. So at the wall, the convection terms will be 0. So inertia, these are also called inertia terms. These will be 0. Why? Because fluid is not moving at the wall. There is no inertia. U and V both are 0 due to no slip boundary condition. Okay, but their gradients could be non-zero. Velocity themselves are 0, but their gradients could be non-zero. Okay, so what will happen is in the momentum equation at the wall, inertia terms will be 0. So only pressure gradient will be balanced by the viscous forces. So at the wall, I'll get that the mu del 2u by del y2 at wall at y is equal to 0 will be equal to dp by dx, and dp by dx can be calculated from the inviscid region velocity minus dp by dx is minus ue due by dx. Okay, so this is how dp by dx is related to free stream velocity. So in the eventually the second derivative of velocity u with respect to y, this del 2 u by del y 2 at wall, is related to dp by dx and du by dx using this expression. Okay, now what can we say about the sign of del 2 u by del x2? So that will depend on the sign of pressure gradient dp by dx. This is the pressure gradient along the boundary layer, or along the flow I should say, not the along movement, because okay, so there could be three possibilities for boundary layer, this pressure gradient within boundary layer. dp by dx could be positive, which is called adverse pressure gradient. And why we call it adverse, we will see that. So in case dp by dx is greater than 0, this del 2u by del y2 also will be greater than 0 at the wall. And what can you say about du by dx? Du by dx will be negative by this relationship. Okay, so if dp by dx is greater than 0, du by dx will be less than 0. That means ue will be decreasing as you move along the wall. So if ue is decreasing, that means the available area is increasing. Decreasing ue means diverging area. A1 V1 is equal to A2 V2. Remember that we are talking about the inviscid core flow velocity. So this adverse pressure gradient will be related to diverging area. Okay, and then this sign also will be positive. Other possibility is that the pressure gradient is negative. Then what will happen? If dp by dx is negative, then du by dx will be positive. Okay, du by dx is positive, that means u is increasing, and that means area is decreasing. It's a converging area. Okay, which area? The area above the body, that is decreasing. For example, you could consider flow around cylinder. So in flow around cylinder, when the flow is approaching the cylinder, there you will have decreasing area, right? As you move along the cylinder, the fluid will accelerate because the available area is decreasing. So that you can say is the favorable pressure gradient region. but as you reach the top of the cylinder, theta is equal to 90 degree, afterwards area will increase. It will be diverging area, and the external velocity will be potential flow region velocity will decrease. So that you can go back and look at the expression for potential flow around cylinder, and you will see that this is happening. Okay, and then in the favorable pressure gradient region, dp by dx is negative, so this will be also negative. Del 2u by del y2 at wall will be negative. And last thing, if dp by dx is 0, then dv by dx is 0, and this thing also is 0. And we have seen this. This is the case of flow over a flat plate. So in the last slide we saw that what will be the value of del 2u by del y2 at wall. So we saw that not at least the value, but we saw that the sign of del 2u by del y2, we could determine the sign of this quantity at wall based on the pressure gradient. Okay, so can we say something similar about del 2u by del y2 at edge of the boundary layer at y is equal to delta? So for that we need to look at the shear stress. So notice that del 2u by del y2 is gradient of del u by del y, right? And del u by del y is proportional to shear stress. Shear stress is mu times del u by del y. So if I investigate shear stress, I could tell the sign of this. What is happening to shear stress? Shear stress at the edge of boundary layer is 0. Okay, so as you approach the edge of the boundary layer, shear stress will decrease towards 0. Inside boundary layer it will have some positive value, and as you approach you will reach the inviscid layer where shear stress will be 0. So near the edge of the boundary layer, what you will see is that del u by del y will be decreasing. That means its gradient will be negative. Rate of change of del u by del y, that should be negative. Then only this will decrease. So at the edge of the boundary layer, del 2u by del y2 will be negative. Okay. So at the wall and at the edge of the boundary layer, we can say about the value of del 2u by del y2. Okay. Now for the adverse pressure gradient, then what we have concluded is at wall this thing is positive, and at the edge of the boundary layer this thing is negative. So at the edge of the boundary layer, irrespective of pressure gradient, we have this thing always negative, but at the wall it depends on the sign of pressure gradient, adverse, favorable, or whatever. So for case of adverse pressure gradient, that means dp by dx greater than 0, at wall del 2u by del y2 is positive, and at the edge it is negative. Now from intermediate value theorem, if this thing is positive at wall at y is equal to 0 and negative at y is equal to delta, then it has to become 0 somewhere in between y is equal to 0 and y is equal to delta. That is from intermediate value theorem, the product of this quantity, so product of this and this will be negative. So if fa and fb is negative, that means f has a root somewhere between a and b, so that intermediate value theorem. So what we can conclude is, for case of adverse pressure gradient, del 2u by del y2 will be 0 somewhere within the boundary layer, that is between y is equal to 0 and y is equal to delta. And when del 2u by del y2 is 0, that means there is a point of inflection. So point of inflection occurs when the second gradient of any function is 0. And what happens is the curvature of the nature of the curve changes from concave to convex. Okay. So what will happen is, in case of adverse pressure gradient, we'll have a point of inflection within the boundary layer, and boundary layer profile will look like a S-shaped curve. So why S-shaped curve? Because S-shaped curve has that point of inflection. From here to here, that changes the nature from concave to convex. So that will happen. Okay. So for adverse pressure gradient, in this figure we show some of the velocity profiles for case of adverse pressure gradient. So if we have a very weak adverse pressure gradient, that means that dp by dx is positive, but the positive value is small, not big enough. So what will happen is, this is the velocity profile, and somewhere within the boundary layer you will have point of inflection. So you see that what is point of inflection, it is going like this, and then it will become like this. So that at S shape we are talking. So this pressure gradient is adverse, but it is not big enough. Okay, so this is how velocity profile will look like. Then what happens, you increase the magnitude of adverse pressure gradient. So as you increase, velocity profile will start becoming looking like this. And at a particular what you call a critical adverse pressure gradient, the velocity profile will become like that you have zero shear stress at the wall, and that will happen when this velocity is going like this. The slope is 90 degree. Velocity profile is almost vertical at the wall. Okay, and if we increase this adverse pressure gradient beyond this critical value, then this velocity profile will become like this S shape that I was talking about. So as we are increasing the magnitude of pressure gradient, this point of inflection, this is going up. So height of point of inflection is proportional to, actually we can say, the magnitude of pressure gradient. So when this point of inflection is high enough, what will happen is this S shape will start looking like this, and what you will have is something like backflow. So remember that free stream flow is happening in this direction, and for high enough adverse pressure gradient near wall, you will have a flow happening in the direction opposite to the free stream flow. So that is called backflow. So near the plate or near any kind of body or near boundary, we will have this backflow condition happening for sufficiently high adverse pressure gradient. So this kind of flow is called separated flow. Why? Because we say that here boundary layer has separated. We could imagine that like boundary layer is starting from somewhere here in a rough sense. So boundary layer has separated. We don't have any boundary layer here because flow is happening now in this backflow is happening. Okay. So this is called separated flow region, where there is some backflow happening at the wall. Okay. So you can see that backflow will start when this happens. So what is happening is, as you keep on increasing velocity, the adverse pressure gradient, this slope of the velocity profile near wall, or you can say tower wall, both are related, right? Del u by del y, that will keep on approaching 90 degree, or you can say the del u by del y will keep on decreasing. So this is y, this is y direction and this is u. Slope is this thing, right? So as you increase at adverse pressure gradient, this slope will keep on decreasing, and then eventually you will reach a critical adverse pressure gradient when this slope becomes zero, that is tower wall is zero. If you go beyond that, slope becomes negative, and then you have backflow. So the necessary condition for flow reversal or for separation is when tau wall becomes 0, or when del u by del y is 0. Okay, So to conclude, adverse pressure gradient is a requirement for boundary layer separation or for this separated flow. But you see that with adverse pressure gradient, it is not guaranteed that flow will separate. You need some high enough value of adverse pressure gradient for flow to separate, and the sufficient condition for boundary layer separation is when tau wall is equal to 0. So you can say that pressure gradient is or adverse pressure gradient is a necessary condition for flow separation, and sufficient is when tau wall is 0. Okay. So to illustrate this effect of pressure gradient on and then the effect of flow separation, let us consider a flow in this geometry. Say this. So this is like a converging and diverging channel, a converging diverging channel. Okay. So this is the nozzle area, this is the throat area, and this is called the diffuser area. Okay. So nozzle area is where area is decreasing, and diffuser area is where area is increasing, and throat area where minimum area occurs. Okay. So in this flow is happening. So when flow is happening, there will be some boundary layer at the walls, and this area in the nozzle region you have decreasing area. That means the in-viscid pore velocity will be increasing. So that is the favorable pressure gradient situation. Here dp by dx will be negative. So in the favorable pressure gradient region, there will be no flow separation. The boundary layer will be attached with the wall. Okay. And as you reach throat area, so at the throat you can see that the rate of change of area will be 0, somewhere here. So there dp by dx you can say is 0, constant area. Still that is not that will not result in flow separation. Okay. So nozzle flow is in favorable gradient and never separates, nor does the throat flow where pressure gradient is approximately 0. So both in nozzle and throat there will be no flow separation. But as you reach the diffuser area, the diffuser section, so area is increasing. That means U will be decreasing, UE. So that is the adverse pressure gradient condition. dV by dx positive. So here there could be flow separation. Remember that this is the adverse pressure gradient condition. There could be if we have sufficient adverse pressure gradient, but whether it will be there or not, that depends. That we will know when tau wall becomes 0. So the expanding area diffuser produces low velocity and increasing pressure. That is adverse pressure gradient. So if diffuser angle is too large, this angle from the horizontal. So if the diffuser angle is too large, so if you have this diffuser angle small, that means the rate of change of area is less. So accordingly, dU by dx will be less. So dp by dx will be less. Similarly, if you have a larger angle, then dA by dx will be large. That means du by dx also will be large, and proportionally dp by dx will be large. So for a larger diffuser angle, the adverse pressure gradient will be large enough so that flow can separate. And you see that somewhere here flow will separate, tau will become 0. Okay. So when designing this diffuser, if we do not want flow to separate, we need to keep diffuser angle small enough so that there is no flow separation. Now this why we are studying this flow separation. So flow separation is very important in explaining the lift and drag forces on objects that we observe in practical conditions. So recall that when we studied flow around cylinder using potential flow theory, then we found that the pressure coefficient on the cylinder is given by this expression 1 minus 4 sine square theta, and this is symmetrical. So if we plot this Cp on the cylinder, we got this curve. This is the pressure coefficient. So from potential theory, we get a symmetric pressure distribution on the cylinder. So this theta is measured from this side, like this. So flow is coming like this, and then imagine here is a cylinder and flow is going from left to right. Then theta is measured from here. 90. This is 90 degree, and this is 180 degree. So you see that around 90 degree you have symmetric pressure distribution. So from flow potential theory, we get a symmetric pressure distribution, and therefore this will result in zero net pressure force on the object in any direction. So therefore for cylinder from potential theory, you'll get that lift and drag forces are zero. But in the realistic case, like in practical conditions, when we measure forces on cylinders, we get a force, and the reason for that is flow separation. So when you actually measure the pressure on a cylinder, this is what we get. So for laminar flow case, okay, so when there is a laminar flow around cylinder, then the pressure distribution is like this. So pressure decreases, just like the case of potential flow theory, and then when it starts going back, flow separation happens, and that causes that recovery of pressure doesn't happen due to this separation. And since this recovery cannot happen, you will see that there is a net pressure difference between front side and back side. That creates a pressure force. So you see that on the back side of the cylinder from 90 to 180 degree, this side, their pressure is much smaller than compared to front of the cylinder. So this lower back region, lower pressure region behind the cylinder, this is also called the wake region of the cylinder. So this is the region after flow has separated or boundary layer is separated from the cylinder. That region is also called wake region, and due to much smaller pressure in the wake region as compared to frontal pressure of the cylinder, this will create a net pressure force on the cylinder that will lead to lift and drag forces on the cylinder. So you see that due to that very thin layer on the cylinder, the delta, thin boundary layer thickness, due to that thin boundary layer that forms on the objects, and then that thin layer separates from the objects, that flow separation is responsible for creating this net forces on the cylinder. You see that the most of the flow is still potential flow around the cylinder, because you imagine that this cylinder is in a very big flow domain. So most of the flow domain is in viscous region. Due to just viscous region near the cylinder, this net forces are coming. Okay, and then also, like, if we increase the Reynolds number and we measure the turbulent flow region, so if flow is turbulent, then also pressure variation is like this. So it's definitely different from laminar, but it's also different from this case, potential flow case. And here also we have flow separation that results in a lift and drag force on the cylinder. But you will notice that in turbulent case, the pressure in the wake region on the back side is higher as compared to laminar case. Okay, and separation also occurs at much larger or much later, you can say, on the cylinder. So separation here occurs somewhere close to 90 degree, and here it is occurring somewhere close to 120 degree. So in turbulent flow, flow separation occurs at much higher or much later, you can say, as we are moving along the cylinder, and the wake pressure is also relatively larger as compared to laminar case. So that results in smaller lift and drag as compared to laminar flow. So to conclude, for case of flow around cylinder, turbulent flow will have much lesser drag as compared to laminar flow, and all this is happening due to boundary layer separation. So then any body of any arbitrary shape, when it is kept in a free stream, it will experience lift and drag forces because of that, because of what we just saw. From potential theory, if you keep any image body in a flow, the net force comes out to be zero. But due to this flow separation, boundary layer separation, there will be a net lift and drag force on the body. So there are certain conventions to describe different forces. So for example, this is an arbitrary body, okay, kept in a free stream. So there is certain conventions to describe different forces. The force acting on the object along the flow is called drag force, and any moment about that drag force axis is called rolling moment, okay. And then force perpendicular to that drag force is called lift, okay. And movement about the lift axis is called yaw movement. And in case of three-dimensional objects, there is this side force, and movement about that is called pitching movement, okay. Pitching movement, and this kind of rotation motion also will be called pitching motion, okay. So if you have an aerofoil in this 2D plane, okay, and flow is coming like this, so lift will be in vertical direction, drag will be in along the flow direction, that you can say x direction, okay. And then pitching motion will be motion like this, motion about z axis, okay. And then the drag coefficient, I think we already, I don't remember whether we have seen this or not. I think we have seen this drag, I think we saw this in the Blasius solution case, that the drag coefficient is defined as the total drag force divided by half rho u square into area. Rho is fluid velocity, u is free stream velocity, fd is the drag force, and a is some characteristic area that depends on the problem to problem, okay. And similarly, lift coefficient will be defined. There here we will have lift force. So this is just to show you the convention of different forces. Different names are given to different forces. Just for your information. Now that area in that last formula or the drag coefficient can be of three types. It could be frontal area for the body as seen by the stream. So if a stream is coming like this, then whatever area that fluid stream sees, this area can be that area. So for example, you imagine you have a cylinder and fluid flow is happening. So for flow will see, if your flow is looking at the cylinder, the frontal area will be simply the diameter, projected area along the flow direction, diameter. And if cylinder has a length L along the z direction, then the frontal area will be simply diameter into that length. That will be the frontal area, okay. So if we are studying problems like that, cylindrical bodies, then we can use A as the frontal area, okay. So this is suitable for thick stubby bodies such as sphere and cylinder or car or trucks, Okay, so it depends, this area depends on what kind of body we are studying. So okay, and this is just has been defined in the literature like that. So if you are studying flow around cylinder, flow around aerofoil, flow around a car, then when we are defining the drag coefficient, we can just say the projected area of that object in the definition of drag coefficient. On the other hand, if we are studying objects which are flat, for example, I have a very thin plate kept in a flow, then its frontal area will be very small, right? Because it's very thin plate, negligible thickness. So in that case, we cannot use frontal area. So in that case, what people use is uh, the area seen by the above, seen from the above. So you imagine flow is happening, you look at the body from the top. So for example, if you have a very thin plate in a flow, then the area of that thin plate will be in my area. And I think I did a mistake. So for example, when we study aerofoil, so I said for aerofoil we can use frontal area. That is wrong, because aerofoils are also very thin. So for thin aerofoils, instead of using frontal area, which will be very less, sometimes people use this plane form area, which becomes the chord length times their length in the z direction. Then another type of area could be wetted area, which is customary for ships. So that is like, if a ship is floating in water, then what is the area wetted by the water? Okay, so these are the three types of area that could be used in the last definition of drag coefficient. But okay, so most of the time you will encounter these two types of bodies, either bodies which are very thin, flat bodies such as wing or hydrofoils, or bodies which have sufficient thickness. In that case, you will have frontal area. Okay, so okay, so that is all. With that, I will stop.